Hello, everyone. So today I want to talk about the structure part. So for the structure part, I was actually really hesitant to make a short video for this topic because I feel this topic is not something that I can explain in a clear way just by a short video. So it's either you have very strong foundation in structure part and you do not need my help, or if you don't know structure part, my video probably cannot like help you understand structure part in a within a limited time. So I originally didn't plan to do the video for this part, but during my office hour last week and yesterday, I still got some question about the structure analysis part. So I feel some groups still feel a little confused. How do we actually need to do the structure analysis? Because we want to be practical, we cannot do like really have a structure analysis at every point of the whole structure and see what is the highest stress level or everything. Or so for our design class this semester, since we have so many topics to cover, I want to make it like a very practical way to do. So we consider a critical environment and a critical component and do a structure analysis specifically for that component in that situation. So I will show you an example later, and hopefully through this example and through today's video, I can give you some guidance on this structure analysis. But of course, there's no way that I can help you understand the structure part as a whole through this video. You need to have some foundation on that, and you need to do. If you forget a lot of the basic things, you probably need to go back to your original textbook to review them. So let's get started. So of course, for each topic, as I always said, there should be a big picture. And for this one, of course, first we need to configure the space vehicle. So this configuration, the structure configuration, is actually not. I don't think it's a job that is done in the structure part. It's done. It's dependent on the other part. Like it's a crewed mission. You need to have a pressurized crew compartment. And you need to have a space for life support and food and everything. And you have a place for if you have rover, and you have place, you need to have place where do you want to put the engine, where is the propellant tanks, and what is where do you want to put the let's say if you use battery or you use solar panel, everything. So the configuration, structural configuration, is basically dependent on all the other topics you have already done, and you want to put in a nice way to configure your EEV. So that's also why we put this part as relatively later part of the semester. So I think for now, you probably already have your own configuration of your own BEV. So this is the first step of the structure design. And then we need to know the requirement of the general requirement of our structure design. So basically, what is the maximum loading that we expect to have? So for our mission, for example, we need to, it's a crew mission with 2 astronauts. So we can have a rough estimation what is the total weight, and that weight could be our loading for our structure analysis later. And also during the mission, what is temperature change variance? So this may cause a this thermal cycle may cause fatigue cycle for our structures, and things like that. And once we have the a general requirement for our structure design, we also need to know for our crewed mission, how it affects our design. So for example, safety factor for the crewed emission should be higher than uncrewed emission, right? And so if we know the configuration, we know the requirement, we know the our mission environment, everything, then we can use them as a guidance to select material, what material we should use for given load, for given environment, and what should be the construction method. So for example, you can use monocoque, some group use semi-monocoque, you can truss structure if that is possible, things like that. And method attachment, you can, for metallic structure, you can use welding, you can use fasteners. For composite material, you can use the bonding. So this is like, okay, based on guidance, is the actual design of our structure part. And so this one is also included the ground test, but for our design, I don't think we need to include this one, but if you want to go fancy, of course, go ahead. And then a very important part. So this part is the structural, is the actual structural analysis part. So we have our material we choose. We have, so we know the yield strength of a material, the ultimate strength of a material, and based on the loading condition, which is based on the mission, we can estimate the loading condition, and we need to calculate what is the stress level in our actual design and if our structure will fail. Or we need to use this information, we use this structure analysis to optimize a structure. Let's say for a pressurized vessel, we need to optimize the thickness of the fixed skin to make sure that, well, it is safe. Let's say if we use safety factor 1.5, it is safe enough to have the 1.5 safety factor, but we don't want to go over thick to cause extra weight, unnecessary weight, and increase cost. So in the end, it should be a optimized thickness, optimized structure. And of course, in the end, there is always mass estimation, cost estimation, and risk estimation. And every design, it always involves iteration. So if it doesn't satisfy, we may need to do some compromise in some part and do some iteration. And in the end, we have our optimized structure design, which is safe enough, but also with minimum weight. So this is a big picture of the structure. And now let's see the some characteristics required for the space structures. So as we can see here, for a complete structure analysis, of course, all these are very important. First, strength. We don't want our structure to yield, or if we have like sensor optical alignment requirement, or we don't want our structure to collapse, or for the buckling analysis, or in the tensile stress, we don't want it exceeding like the ultimate strength, which will cause a rupture of the structure. So that is a strength part. And the structural life is more like a fatigue analysis. So for the material we select, we have the structural toughness. And if the crack propagate to a certain level, the fracture toughness of that crack, if it greater than the threshold, the fracture toughness of the material, it will become unstable and it will cause failure of the structure. So this is kind of my PhD research. And also several years ago when I taught Mech Design 1, I spent like about 1 month to talk about the fatigue failure in the aircraft structure. So for this one, I would say it is important, but let's be practical. I do not require you to do a fatigue analysis of our structure to see, okay, under the vibration, under the fatigue loading, if your structure really safe, if you really, the structure of the EV can really survive the 30 days mission without the crack existing on the EV exceeding the unstable phase. If you want to do that, absolutely encourage you to do it, but it's not required in this class. So this is the fatigue analysis, and the natural frequency is basically, let's say in the end, let's say if we launch the EV from the Earth, and the fundamental frequency of the coupled payload, which is our EV and the launch vehicle, should be outside the range of the frequency of the launch vehicle control system. So it will not cause the excessive loading, vibration. And this is also a very important structural analysis. And again, it's not required in for this semester. And positional stability and stiffness here, I think these two is more like closely connected to each other. It's more like the deflection and the loading. So for example, let's say we put the EEV into the launch vehicle, and let's say somehow the EEV is like the size of the EEV is somehow just fit into the launch vehicle, the cargo bay. And during the loading, let's say during the launch or loading, we want to make sure that the deflection of the EV should be still within the internal space of the launch vehicle, which is sometimes we call the dynamic envelope, which is envelope after deflection and the loading. So this is also an important analysis for the structure part. And also we want to make sure that if we have sensors, optics, or antennas on the AAV, we want to make sure that, well, if there is a deformation, we want it to not cause the misalignment of the sensor, optics, or antennas, otherwise it won't function properly. So these two are more related to the deflection part. So of course, math is always required for every topic. So for this one, I would like to put in this way. So I would consider strength is always most important. Deflection, if you want to go further, work on the deflection. And then if we want to do more, do the fatigue analysis and natural frequency and positional stability. So for these five subtopics of the structure part, all of them are important, but I think this is the importance level from my opinion. And for this class, this is the only one that is required. But of course, if you want to participate in competition, or if you want to go fancy for any reason, you can add stiffness, deflection analysis, fatigue analysis, natural frequency analysis, add them in. And if you want help on the deflection and the fatigue analysis, I can help, but I cannot cover it in this video. It's going to be too much. So I will only focus on this one. If you need help on this part, you need to email me so we can schedule a one-to-one Zoom meeting, and I can talk to this part to you in detail. And so this is the potential critical environment that a spacecraft structure may experience. So as I said, for our structure analysis, we need to determine a critical environment and a critical component. So what is the most critical situation that your EV will suffer? And under this situation, what is the critical component, which means that component will fail first if it causes failure. So if we can identify the critical situation, critical environment, and critical component, we focus on structure analysis on that component in that situation. So we can make our analysis much easier instead of showing stress level at every point on your EEV. So we do not have so much time on that. So for the potential environment, first one is it starts from the manufacturing. So let's say if you, I don't know if any of you has internship somewhere and saw some like the welding process. Actually, the welding process is done by having the high temperature and kind of melting the metals. And that process actually changed the material property. And most of the time, it will cause a residual stress at the welding place. And that place can be a problem place in the later use. So a lot of times that is the weakest place of the structure for the welding place. And also for the, well, I was a aircraft structure engineer before I came to UF. So from what I seen was that the major problem of aircraft structure failure was well, one is a corrosion, one is a wide spread fatigue crack. So for the crack, the majority crack was originated around the fastener holes. So when you, during the manufacturing process, when you drill the fastener holes, the fastener hole itself is not perfect. And there's always some micro crack generated during the manufacturing process. And that micro crack is the potential initial crack during the fatigue loading. And we want to control in the whole aircraft lifetime to make sure that that fatigue crack will not grow into the unstable phase. So we can see that the critical environments start from the manufacturing process. And in the handling and transportation for spacecraft and also ground test is also very important. And I think the example I will talk about later is we consider the launch, landing, and in space when the internal pressure, consider the pure internal pressure. So because during the launch, there's you can imagine it's the highest acceleration there. So that acceleration probably is also the time that launch and landing is the maximum load factor that a spacecraft ever experienced. So it's very common to consider the launch and landing as the critical situation. And another situation for the pressure vessel is that during the flight, the internal pressure, where we want to make the crew feel comfortable. So internal pressure is still same as on Earth, but the outside pressure is 0. So the pressure vessel, when you consider if your structure is safe enough to not exceeding the yield strength with specific safety factor. So these are the 3 situations we consider as a critical situation for the example problem I will talk later. For our design, however, of course, our EV will launch from the Earth, but if we need to bring the EV back to Earth and landing on Earth, and landing on Earth with structure integrity so that we can reuse it, this is a part that the AIAA didn't mention. The whole document doesn't mention that if we need to bring the EV back to Earth with structural integrity. So I would consider we do not need to consider this part for our design. Well, if you have your own understanding, of course, go ahead. But this is just my personal understanding. And I also sent an email to the AIAA, but they didn't reply. So from my point of view, we do not need to consider bring the EV safely back to Earth and expecting to be reusable. So probably launch is a critical situation. Well, you can have your own opinion. This is just my personal opinion. I don't want to force it onto any of your groups. And mission operations, of course, it has the it also has acceleration, and of course, let's say if you consider docking, during the docking, it has the maximum load applied, or if there is something like impact from the materials. So well, you have your own. Your group should have your own opinion. What is the most critical situation for your EEV, and make it clear, justify your conclusion. I don't know what happened. Sorry, wait for 1 second. Something wrong with my iPad. Okay, now it's back. So this is about all the potential critical environment. And this one it shows how the crewed mission influenced the design of the structure. So of course, if it's a crewed mission, it needs to be pressurized. And of course, you need to have the place for food storage, waste disposal, temperature, everything, and vibration, noise, moderate noise. So probably you already consider this part. In the life support, environment control life support system. And for our EV, we don't have re-entry. And it's also say that we need to have the viewpoint for the people, if it's crewed mission, so they can see outside. And this is I will show you some basic information of the structure analysis here, so we can use it for the later structure analysis. So let's say if we have the metallic material, you probably have this is for aluminum. It has a proportional limit. Majority time we want our structure to operate within the proportional limit. And with 0.2% setup, the plastic deformation, there is a yield strength, and this is actually the arming strength when it ruptured. And if it's steel, some kind of steel, it has a dip after the yield strength, and then it ruptured here. And for some brittle material like the glass or ceramic material, it just there's no yielding or anything. It just go through this linear region and then rupture and break directly. So this is the basic information of the structure, how it will fail for different types of materials. And of course, you should understand the Young's modulus is basically the, let's rotate so we can see the whole thing. The slope here is Young's modulus, and atomic tensile strength is here, whatever is highest. And the proportional limit is when your structure is deformed under the inelastic range. And also the fracture toughness is for fatigue analysis. So it's a threshold that before your fatigue crack become unstable. So these are the basic concept of structure analysis. And for the material selection, we can choose metallic material. The most common one, they are the aluminum. Of course, they have a lot of advantages. It is like a affordable material, and the strength to weight ratio, it has the best strength to weight ratio is you can, well, Starship also uses steel. So, well, in terms of strength to weight ratio, it's not as good as aluminum, but I think they use the steel for stainless steel for the structure part is mainly because the heat shield, because the thermal conduction of the aluminum is much higher than a steel. So if we use aluminum for the re-entry or entry, we probably need to have a much thicker, heavier heat shield. But if we use steel, we can actually make our overall structure lighter because the thermal conduction. So, and of course, that's what they originally plan to use the carbon fiber composite, and they changed the steel probably because of cost. Because the carbon fiber composite is much more expensive. Where composite structure can be cheap if we produce, if it's like we make something in large volume. But if you just make one, the total cost can be very high. So you should have your own decision and your own justification which material you want to use. And for specific, let's say for aluminum, we have different type. We have the 7075 or 661, or on the aircraft structure, we also use, a lot of time we use 2024. So you need to have a specific, you cannot just say aluminum, which type we have. And different type of aluminum really have very wide range of property. So the yield strength, the Young's modulus, yield strength, and everything, tensile strength, they are quite different. And so you really need to have a specific, what kind of aluminum or what kind of the steel material. So this is the material property for each specific material. Some of data we will use later in the example. And for the type of structure, as I said, you can use the truss structure. So this one is basically mean that, okay, all the for each truss member, the force is only actually either tension or compression. This is the most simple structure. And for our pressurized vessel, we can use monocoque cylinder, which basically it's just a skin. It's a fuselage skin, and it's pressurized inside. And we can also add the stringer and a frame internally. So it seems that it makes our structure more complicated, but if you learn the structure optimization before, you should know that adding this frame and a stringer inside this internal supporting structure actually can decrease the total mass of our total structure, because when we use the stiffeners inside, when we use the stringer and the frame inside, we can make this fuselage skin much thinner. So and the stringer and the frame become the load carrying structure. And so in the end, it's more like an optimized structure that we have specified a component to carry the load, and the structure is more optimized and weight is lower, it's reduced. So a lot of times they use the semi-monocoque structure, and beam and plates, well, a lot of times we simplify them as beam component or plate to simplify the calculation. And for attachment method, as I said, we can use fasteners, we can use welding. Welding is very popular if it's pressurized vessel, because, well, it's easiest way to maintain the pressure inside. But I would like to say that it's not the only way, because if you see the aircraft structure, actually majority of the aircraft structure, they use the rivet. So if you use a fastener and there's a sealant between the fastener and the let's say the fuselage structural frame or stringers, it can also seal the fuselage properly. And a benefit of using fastener is that it's much easier to repair if there's something damage that we want to repair. Fastener, you can easily remove it and attach a new one. But if it's welding, it's really something like you need to put your EV at a specific location and use specific equipment. The repair part is not that convenient as the fastener. And if you use composite material, of course, majority of the time we use the adhesive bonds. So based on your material selection, structure, and every type of structure you use, and you can select the best attachment methods for your structure. And this is basic information. I'm pretty sure that you all learned this in either mechanics materials or a VA class, or I think there's a class called aero structure. For different boundary conditions, for example, clamped, simply supported, and different loading condition. For example, this one is the concentrated force in the middle, and or distributed force. We have different reaction force, different maximum bending moment, and different deflection equation. And this one, if we can simplify our structure analysis in this way, we can use this conclusion directly. And you will see later that this is the one that we will use in our structure analysis later. And also, this is the moment inertia moment inertia for different cross section, and solid, hollow, and this is a thin wall structure. And again, this is the one that we will use later for our structure analysis. And also pressurized vessel, we need to know how to calculate the longitudinal stress and hoop stress. So this is how we calculate. This is the equation for longitudinal stress, and this is the equation for hoop stress. One thing I forgot to mention, I probably should say that at the beginning. For our structure analysis, you can go fancy to use any software you want to use. Just make sure that everything is, the result generated from the software is reasonable. Because a lot of times when students, in my FE class, it often happens with that, or often happening that they didn't do the preliminary analysis, the hand calculation to know the approximate range, and they do it in the abacus directly, and they can generate very beautiful contour plot and stress of the stress level and everything. And they feel, okay, great, we generate very beautiful result, and they consider that is the exact result. And that can cause a lot of problem, because if a single mistake in the input in the abacus, it can generate a very weird result. And if you don't have solid understanding of the structure analysis, and you don't have the preliminary analysis, you have no idea if the end result makes sense or not, because whatever you see is just a high stress level and a contour plot, and you feel it's correct. So what I want to say that I don't have a preference, like you have to use software or you have to use hand calculation. You can do either way. Hand calculation is good enough. And if you want to use software, any software you want to use, Abacus, ANSYS, SolidWorks, and can also do the stress analysis. It's also okay, but make sure that the result generated from software is reasonable. So if it's like several order magnitude off from the actual stress handle calculation, it means that your software result is wrong. So this is something that we want to make sure in your structure analysis, don't just show a beautiful picture, but the result doesn't make any sense. So this is the equation to calculate the longitudinal stress and the hoop stress. And this is for the buckling, because we know that during the launch and landing, the pressure vessel will experience the compressive stress, huge compressive stress. And we need to consider if it will cause the buckling of your structure. So for the monocoque cylinder, this is the equation we use to calculate the, well, if the stress higher than this one, your structure will buckle, which means fail. So in this equation, this is the buckling stress. We can consider it a threshold stress. You want to make sure that stress generated in your structure is lower than this one. And this is the plasticity correction factor. And for our material, we use 1 to simplify the calculation. And this one is correlation factor to match the theory with the test result. So for because our purpose is for rough sizing our structure and the compression and bending loads, use gamma equal to 0.5. And E is Young's modulus, of course. T is the thickness of the monocoque cylinder, is the thickness of the structure. Now let's see our case study, the most important part of this video. So the case study is a crewed module that transports astronauts from the Earth to the lunar orbit. So it's not the same, but hope you can find some useful information from this case study. And from all the other topic, they have already done, the estimated gross volume of the crewed module is 85 meter cube. And so they use the diameter about 4,000 millimeter and the length 6,000 millimeter. And total mass, the estimate is 11 ton. And material, they use CC61T6. T6 is the heat treatment state. And they use the solid skin monocoque. And attachment method, they use welding. Of course, the textbook shows a lot of justification of everything, but for this video, I don't think it's necessary to waste a lot of time talk about why they choose this material, why they use this structure, why they use the attachment method. But in your report, you should have that. And for this material chosen, the tensile atomic stress is 290. This is also very important information for our to decide if your structure will fail or not. And for the pressure vessel, the maximum internal pressure is 0.1096 megapascal. And safety factor, if you use the arcing strength, use 2. If it's use the yield strength, use 1.5. So the goal of this structure analysis is to find the optimized shell. So basically, it means that it needs to withstand the total weight or the load factor I will show you later to make sure that it is safe based on this safety factor. And at the same time, the thickness should be minimum to satisfy these requirements. So then we can call it optimized structure. And the critical situation they consider is because for this case study, they need to bring this crew module back to Earth with the astronaut inside, and the crew module itself should be reusable. So it should landing without any structure failure. So to consider 3 situations: launch, landing, and also one situation is in space. The internal pressure this is the internal pressure, and outside pressure is 0. So with this maximum internal pressure, if the structure is safe or not, or with this internal pressure, what is the thickness, and during the launch landing, what is thickness, and we choose whatever is highest. So it can save for all three critical situations. So this is the basic idea of the structure analysis. And this is a general configuration of the structure. So they have the engine here, and this side is the docking, and have window, viewports, and airlock here. And this is a more detailed configuration. So this kind of pin kind of thing is for the spacecraft, for this crew module, because they want to put this crew module in the cargo bay of the space shuttle, and use space shuttle to bring this crew module to the lunar orbit and then bring back to Earth. So the load factor of the space shuttle is transferred to the crew module through this pin, and this concentrated force applied by the pin to the crew module is transferred by this ring. So it becomes distributed force to the crew module. Now, let's say for these three situations, maximum internal pressure, landing, and launch, we start from the maximum internal pressure. So basically, this means that in space, we have this much internal pressure inside this thin wall pressure vessel, and we want to find the optimal thickness to make sure that the structure will not fail. So for this one, what we want to calculate is that the hoop stress, well, it has a hoop stress, it has a hoop stress, and it has longitudinal stress, but we know that the hoop stress is double of the longitudinal stress. So hoop stress is the critical stress here. So that we want to make sure that the hoop stress is smaller than the allowable stress, allowable tensile stress. So for the material they use is 290, and because this is animal strength, so they use safety factor 2. As I said, if you use yield strength, it's also okay, use 1.5. If you use animal strength, use 2. And the internal pressure, this is maximum internal pressure, and this is the radius of the crew module, because at the beginning, the design that the diameter is 4270, so the radius is 2135, and this is the ultimate tensile stress. So extra stress caused by the internal pressure should be smaller than the allowable tensile stress. Allowable tensile stress with safety factor 2. So in this calculation, the thickness of the thin wall pressure vessel is 1.61. So we would say that, okay, for this situation, this is optimized thickness for our structure. And now let's consider the launch and landing. And of course, as I said, for the launch and landing, it has a very strong, large compressive load on the structure. And this is the load factor in 3 directions for space shuttle. And of course, this load factor will transfer to the crew module through the attachment, right? So we should expect that the crew module should have the same load factor, as listed here. So we use this load factor to consider, okay, under this load factor, what is the maximum compressive stress in the structure, in our crew module? So now this becomes a combined loading problem. So first, the load factor in the Y and Z direction will cause bending. So I can use this one. Let's say this is a let's assume that this is a pressure vessel. this is the spacecraft, the crew module they want to launch or landing. So if we have the load factor in the lateral direction, and we can consider the combined load factor in the lateral direction, which is this one, becomes the maximum bending moment. And if we consider the whole pressure vessel as a beam problem, then it becomes the bending moment. We can use it to calculate the bending moment. So this is how we calculate the bending moment. So this is the weight, and for our, well, we consider, as I said, we use this one. We consider is a uniform distributed load for the pressure vessel. So this W is the weight per unit length, and weight per unit length. So this one is the total weight, and this is the length in this X direction. And combine the load factor in the Y direction, which is the maximum load factor in the lateral direction, and this becomes the maximum bending moment. And of course, if we have the maximum bending moment, the compressive stress, the maximum compressive stress caused by the bending moment is easy to calculate, right? The very basic equation you learned in the mechanics materials, MC over I, maximum bending moment, C is the radius, and I for the thin wall pressure vessel, as I put it here, this is the moment inertia of the thin wall pressure vessel. So basically we can ignore the thickness. If the thickness is relatively large, we need to use this one. But if the thickness is much, much smaller than the radius, we can use this one. So for our example, of course, it's the thickness is much smaller than the radius of the pressure vessel. So MC over I. This is the maximum compressive stress. And also, it also has a load factor in the X direction during the launch, during the landing. So that is a pure compressive force, right? Let's say we have force in the X direction. So we can consider that, okay, this compressive force will cause a compressive stress. And this one, we consider it a PC. So basically, because the load factor is given as a negative value, so it had, well, when you calculate, you know what it means. So this is compressive force, and this is the cross-section area of the thin wall structure. So it's basically the area that carry the compressive force is the area here, 2 pi r times T. So we add this one, times safety factor 1.4. So this is a compressive stress caused by bending, compressive stress caused by compressive force, which is X direction. And another thing we also need to realize that for the differential pressure during the launch and landing, depending on different situation, the differential pressure changes. So the height can be, so for example, during the launch, the height can be this value, and this is the lowest value. So it basically means that in some situation during the launch, probably the outside pressure is higher, it's a little bit higher than the internal pressure. And this can also cause a compressive stress. And this compressive stress, this time, of course, we only consider the stress in the longitudinal direction. So it's the PR over 2T. And you can pretty much ignore the sign here, because when you calculate, you add all of them together. But this one, they use negative sign because the P has negative value. So they put the negative value here. Basically, you should understand it in a way that it's a compressive stress caused by bending, compressive stress caused by normal force, and compressive stress caused by the internal pressure. here is a negative internal pressure. So we add all three of them together. And this total compressive stress should be smaller than, remember the equation I just talked about? This is threshold to cause a buckle. So we want to make sure that this stress will not cause it to buckle. And based on this equation, this situation, we calculate, of course, during the launch, during the landing, they have different load factor. So we calculate the thickness, the optimal thickness for launch situation is 2.57, and for landing is 2.55. It's very close, but of course we know that choose whatever is highest. And compare with the pure internal pressure in space, the maximum pressure in space, 1.61, we know that in the end, we choose 2.57, whichever is highest, so that your spacecraft, your EAV, can survive all different situations without any failure. And in the end, they also did an extra step to make sure that, okay, for the stress, if we plug in 2.57 here into the equation over here, both sides the same. We want to make sure that this stress level is not big enough to cause the structure yield in compressive load. So compressed proportional limit of this material is 190. So it's not just want to make sure it doesn't buckle. We also want to make sure that this stress is within the proportional limit. So they plug in 2.57, which is the thickness we find, the optimized thickness we find here, into the equation and calculate, okay, this one is way lower than 190. So it's just a general idea that in your structure analysis, it always buckle first and then has actual yielding problem in compression. But this is just one step to make sure that it's safe in all situations. So this is for, of course, this is for a spacecraft that is launched from the Earth to the lunar orbit and bring back safely to Earth. Is not the same as our EV. And also, I got a question yesterday. So this is a monocoque structure. And one group yesterday told me that, what if they use semi-monocoque? How do we do the structure analysis? Then if you use semi-monocoque, the idea can be similar. The calculation is a little different. So basically, for the semi-monocoque structure, we can simplify in a way that all the stress is carried by the stringer. So all the hoop stress is carried by the frames, and also longitudinal stress is caused by the stringers. So basically, you want to make sure we can kind of ignore skin, the FISA skin. They are not a load carrying structure anymore if we use semi-monocoque. So in that situation, we want to make sure that, okay, let's say if you also consider launch is a very critical situation for your EV, then we want to make sure that that compressor stress, the total compressor stress, will not cause a stringer to buckle. And if you want to do same situation like this one, when your EV in space, the maximum internal pressure will not cause the yield of the frame. So frame becomes the load carrying component for the hoop stress. So it's not the same, but you can consider kind of similar. So this is everything I want to talk about for the structure analysis, but of course, this is hand calculation. You can also use any software you want to use, just make sure the result is reasonable, because I have seen so many times in FEA class, in aircraft design class, they show very beautiful picture, but the result doesn't make sense. And they just say, I don't know, this is what I generated from Abacus, or this is what I generated from the SolidWorks. And they didn't have understanding of the actual structure analysis, just show the future. We just want to prevent that. So you can do it in any way you want, hand calculation or software or anything. Just make sure that you actually understand the structure design, the structure analysis. If you have any question, you can always ask me during my office hour or email me, and I will post this document on Canvas soon. Thank you and good luck.